Last time we talked about the paper written by Lam and Yao named The Estimation of Latent Factor for High-Dimensional Time Series. In that paper, we assume the number of factor R is known and fixed, which means the population version matrix L is of rank R. However, in practice, generally we do not know the value of R. Instead, we need to estimate this number. In order to deal with this issue, Professor Lam and Yao proposed a ratio-based estimator. Which is given by we search a positive value which minimizes this ratio, because in many cases we always observe this phenomenon. If we plot the eigenvalue for that positive semi-definite matrix, we can have a sharp decrease of the ratio, and the corresponding point is generally equal to the rank R. With this phenomena, they propose the ratio-based estimator to estimate the rank R. And in this paper, we will provide some theoretical support for this ratio-based estimator. This video is supposed to be short because we will take advantage of lots of theorem which we proposed, which we already proved in the last video. So I directly copy the assumption in this video to save time. The key difference between these two papers is that in the biometrical paper, estimator of latent factor, we assume two scenarios. One is weak cross dependence. Another is strong cross dependence. But in this paper, we only deal with the assumption 6, which is weak cross dependence. Means that the cross dependence between the latent factor and the white noise is of little order of factor strings. Let's start our proof. The theorem 1 given in paper tells us the convergence rate for the eigenvalue to its population version. This theorem gives asymptotic property, which is And for eigenvalue r plus 1 to p, because the population version of rank for matrix L is r, so the eigenvalue which less than r's eigenvalue is equal to 0. By this theorem, later we will see a corollary which states the convergence rate for that ratio goes to 0, which provides the theoretical support for this ratio-based estimator. First, let's prove this theorem. From previous biometrical paper, we know that the perturbation for matrix L is given by Then let's do the first case. Here I use the notation gamma g hat and aj, which means that it is corresponding eigenvalue and eigenvector. Since we already know the perturbation bound for L, also in last paper we know the perturbation for matrix A. We can rewrite this equation in another way, which can take advantage of this bound. Furthermore, I will subtract a population version of eigenvector and add it back. The reason why I do it because the perturbation for single eigenvector is upper bounded by the perturbation for the part of unitary matrix which is formed by first R eigenvector. And we already know the perturbation bound for the matrix A. We can make use of it. Let's go ahead. After some calculation, we get this four term. We call them 1, 2, 3, 4. Let's deal with this four term one by one. Since we know the perturbation bound for L is also from last paper, we know since we have assumptions for the weak cross dependence, this term is equal to big O only related with vector strings p power 2 minus 2 delta. Then the perturbation for eigenvector is given by this result is under the scenario of weak cross dependence in the last paper. So the first bound to simplify our notation, we call this term Hn. Hn is little o1 in the last paper, we know. And in this paper, we still have this. which is the vector strings times hn squared by simple algebra. For each of these 4 bounds, we apply the sub-multiplicity for matrix multiplication. The first bound is same with the third. Since hn will go to 0 as p and n go to infinity, so this term will dominate this term because this is small order. Hence, our bound for the first part of theorem follows. Now let's consider for estimate eigenvalue at position r plus 1 to p. We recall a lemma in previous paper. In the video to talk about that paper, we refer to as it lemma 1. By symmetry, we can get the estimator for orthogonal complement for A. The perturbation for A and perturbation for B are same. So we still have this bound for eigenvector. Let's write down the definition first. We may try the technique we use above, which we can first subtract L and add it back. However, if you do in this way, you can only get the rate which is equal to the previous case for precision before R. And we know this is not fast than the rate we state in the theorem. The reason is that for those later positions, the true eigenvalue is 0. And hence, we have L times eigenvector is equal to 0. We haven't taken advantage of this property, so our analysis for this rate is not sharp. Let's take advantage of this property. First, let's do some calculation on this property. Recall in the last video, we always know the summation of matrix can be write as matrix multiplication, which related to some huge matrix. We put the matrix together column by column and times its transpose. We call this matrix as WK0. Then the eigenvalue decomposition or singular value decomposition for L is UDU transpose, where D is diagonal matrix up to R positive eigenvalue, and others are 0. Hence, WK0 can be decomposed in the following way. Because in the eigenvalue decomposition, the unitary matrix is formed by eigenvectors. For those later precision, the eigenvectors transpose WK0 is always 0. Because this term will give 0. let's come back to our original proof. Let's introduce an intermediate term called L hat. Which is the sample version times a population version. And we write it as matrix modification format. By above analysis, we know that for any vector v, we transpose L hat aj, which can be rewritten as aj transpose w0 times something, which will give 0 always because the previous term is 0. Hence, we perform a similar trick. L delta minus 2L hat. Add back the reason why we do this, because if we expanded this term, we find it equal to when we use submultiplicity, we will see that it is a square of the perturbation for autocurrence for y, which can make the convergence rate faster. By property that Laj is always 0, this term is always equal to write in this way can get faster convergence rate because we have two perturbation. For middle term, we can also add a minus AJ because we show that L hat AJ is also 0. Now we define the first term 1 and this 2 and this 3. We still analyze them one by one. We know the first one can be rewritten as perturbation for autocoherence for y and a square. Which we shown in the last video that it equal to the perturbation bound for error. The perturbation bound for error dominate other term, so only this term is left. And further, if we put some strong assumption on the epsilon, for example, sub-Gaussian assumption, then we can expect to get faster rate, which is theorem 2 we will talk about later. Those bounds are all given in the biometric paper. You can refer to last video to see this bound. All three bonds are same, so we combine them to get for later position of eigenvalue. After we prove the theorem 1, an important corollary comes. Let's write down that corollary, which will give the explanation for the ratio-based estimator. Under the condition of theorem 1, the previous estimated eigenvalue will have same order, but at position R, we will have a sharp decrease because this rate will go to 0, which is hn squared. The reason why this provides the theoretical support for the ratio-based estimator is because from the first one, we know they are almost similar. They are at the same order. But at the position R, it will go to 0. So we can observe a sharper decrease at this position. Let's prove this corollary. In the previous biometrical paper, we know that the factor strings is upper bounded by smallest true eigenvalue, non-zero eigenvalue. And also because eigenvalues are ordered, we know that first R eigenvalue are of order p power 2 minus 2 delta. Also, for I less than R, in theorem 1, we have the perturbation bound. Which is big OP Hn. Since Hn is little o1, this term is little op of vector strings. Hence, we have this and this. Consequently, we know this ratio will go to 0 because the numerator is of little order of denominator, which implied this go to 0 and which further imply they are of same order. So we have of order 1. At precision of a true number of factors, we directly apply the theorem 1, the ratio of two convergence rate. And we know this will go to 0. Now we have proved the theorem 1 and the corollary. And by those theorems, we know the theoretical underpinnings for this ratio-based estimator. But in the same way of the biometrical paper, we know that if we assume sub-Gaussian condition on the noise, we can have the sharper bound. And in this paper, we also have the theorem 2, which deal with the sub-Gaussian case. Further two assumptions. The entry for error IID for different time point and position. The mean for each entry 0 and variance is a finite number. The eighth assumption is identically to the biometrical paper, which is sub-Gaussian assumption. Now we have theorem 2. With assumption 1 to 8 hold. A little bit relaxed assumption. We define Ln equal to p power delta over 2 and over square root n, which gives 0. And we also assume high order, which is same with the theorem 2 in previous video. Let's first look at the first part of theorem 2. The rate of convergence is decreased by a factor p power delta over 2, which is the same with the phenomena we observed in the previous paper. We also have a decrease by a factor p power delta over 2. And for second part, the convergence rate is decreased by a factor p power delta, which is the square of the value which is decreased in the first part. And it is intuitive because the second part enjoy the faster convergence rate, so it should also decrease more. Let's give the proof. In the previous paper, we know the key point is that the rate for the sample version of autocovariance for noise is decreased from p over square root n to p over n. And then the perturbation bound for L changed from Hn to Ln at this position. The Ln is smaller than Hn by a factor p power delta over 2. Also, for the perturbation for B, it is of order Ln. Previous we have order Hn. Then we can just take advantage of previous analysis. Recall previous 1, 2, 3, 4. Let's recall this 1, 2, 3, 4. We change the Hn to Ln, and we know that the first rate curve convergence is also dominated by the 2, 3, and 4. So we will get which is the rate in the theorem. And we can also recall since this p squared over n can all be written as hn square times vector strings. And after the careful analysis, we know those rate will be improved to ln square times the vector strings. So we will get which is decreased by a factor p power delta. And also, we have a modified version of chlorine, which is a modified version of chlorine 1. Follow the exactly same analysis we can get which is of order ln, and will go to 0. Maybe we can do this rate. It is a simple ratio between two rates of convergence. The only difference is the numerator. It decreased by a factor p power delta. We are done. In this video, we talk about the theoretical underpinnings for the ratio-based estimator under the scenario that we have weak cross-dependence. And we talk about two cases. One case is sub-Gaussian and another is not. That is all things I want to talk about about this paper.